with large interaction. Please, Orphée.
Thanks a lot. Thanks for the opportunity to give this talk. So indeed, I will talk about some work I did during my thesis with Giambattista Giacomin, Raphael Greenblatt, and Yu-Yun Hu about the random field Ising chain. Let me say a few words about the Ising model itself. The Ising model was introduced in the 20s to describe a ferromagnetic material. So you can, the model, one way you can model the system is by having atoms positioned on a lattice, and each atom has a small magnetic moment, which is called a spin. And then the spins can interact. The interaction decays with the distance. So for simplicity, you can imagine that they interact only when there are neighbors in the lattice. And the stronger the interaction, the more they will tend to align with each other. So you put these neighboring nearest neighbor interactions everywhere in the lattice. And this gives you an interesting model, which is already difficult to analyze. In fact, in the Ising model, the spins are not so complicated as in this video. They can only be upward or downward. So there are only two values. For us, the situation will be, in some sense, even simpler because we will consider the case where the underlying graph is simply a line. But the difficulty will come from the fact that we add an external magnetic field, which is heterogeneous. In fact, it's going to be taken as a realization of an i.i.d. sequence. But I'm going to define this in details now. So first, let me present the model. And in the first is the pure case, so without the external field. So we have a system of size n, so capital N sites numbered from 1 to n. Gamma is going to be the intensity of the spin-spin interaction, and we are going to consider fixed boundary conditions. So G and D are values in -1 and +1. This means that at 0 and at n+1 we have additional sites where the spins are fixed. Now a configuration on this space is a function sigma, which to every site assigns a spin either -1 or +1. So here is an example. I've used full disks to denote the value +1 and empty disks for -1s. Okay. On this state space, we define a probability measure. So we're in statistical physics. So this probability measure is defined through a Hamiltonian. And then we take the exponential of the Hamiltonian and normalize the measure to make it a probability measure. So the Hamiltonian is defined quite simply. It simply counts the number of spin switches along the chain and multiplies by minus gamma. Then if you take the exponential and renormalize, you can understand this as the fact that the Hamiltonian penalizes every spin switch in the system by a factor exponential minus gamma. The boundary conditions intervene through the first and the last term in the sum. So sigma 0 is equal to G and sigma n+1 to D. So we take into account the possibility of having spin switches between 0 and 1 and capital N+1. And the quantity that makes P a probability is the partition function. It's the sum of the numerators. Some additional vocabulary. We're going to describe the spin configurations as spin domains. So sites, consecutive sites where the spins agree, separated by spin walls. So locations where the spin switches. Okay. In this simple model, the pure Ising chain, everything can be made quite explicit. The model is solvable, and in fact, it's easy to describe. So let's first forget about the boundary condition on the right. Let's remove the last term in the sum. Then I claim that under the Gibbs measure, the walls between n and n-1 and n appear independently with this probability coming from the fact that a wall is penalized with the factor exponential minus gamma. And if you now have the boundary condition on the right, this adds a mild conditioning on the variables which indicate if there are walls or not. But this simply a conditioning on the parity of walls. Okay, but this is only a mild conditioning, and this does not make the comprehension much more difficult. So if you use so in particular, if you let the size of the system go to infinity, so n go to infinity, you end up with a succession of domains which are geometric variables with mean exponential gamma plus 1. Yeah, and you should just keep in mind this order exponential gamma. Now the case of so the random field Ising chain is here is a small you see here is a simulation of the pure Ising chain. So we have 5 independent samples with the conditions plus on each side, which I have not plotted here, but okay. Then we can also compute the probability for every site n of having a spin plus 1 at the site. And in this case, as you can see, in the bulk of the system, the probability is very close to 1/2. In fact, if we had free boundary conditions on each side, the probability would be everywhere 1/2. And here, the boundary conditions have an influence, but only near the boundaries of the system, and the relaxation length is this length exponential gamma. If you want to state this in a slightly different way, you can phrase this in terms of overlap. So if we consider sigma 1 and sigma 2 two independent samples under the Gibbs measure, then this random variable, the overlap, so the density of sites where sigma 1 and sigma 2 agree, this random variable will converge towards 1/2 in distribution as n goes to infinity. Okay. So this situation is very well understood, and now we're going to turn to the random field Ising chain. So we work with an i.i.d. sequence H of random variables. I'm going to assume for now that they are centered, and also that they have a finite variance. For example, we can think of the Gaussian law centered and with variance theta squared. Now, for every realization of this sequence, which is called the environment, and for every parameters, we are going to define a new Gibbs measure by adding to the Hamiltonian an interaction parameter. So the configuration sigma will interact with the external field, so this term. So you see that now the Hamiltonian is a random function, because here the random sequence H intervenes, and also the Gibbs measure is a random measure. So for each realization of H, we consider this random measure, and our aim is to say how the system will behave. So now, again, there's a partition function, which is a random variable. And here is an example. So this is one realization of the Gaussian law, I think, and one realization of the configuration under the law. So as you can see here, we have a small remark is that this term penalizes walls. So neighboring spins are encouraged to agree. However, each spin is also encouraged to agree with the local field. So there are clearly two behaviors which are going to counteract. Here, these two have decided to take value +1, and we see that this corresponds to high values of H. In this region, it's not so clear. The whole region is plus, but there are some arrows going up, some others are going down. But overall, it seems that indeed the external field is rather positive. Okay. Now, the aim is to study the relevance of disorder. What does this mean? This means, does the adjunction of this random external field modify the system and in particular in the limit of large interaction. So we're going to work with this fixed law, the value theta squared, which is kind of the scale of this sequence, is going to be fixed, but we're going to look at large values of gamma. So you might expect that only this term is now important, but we're going to see that it's not so clear, that in fact disorder is relevant. So the questions are, does the disorder change the scale of the domain rule structure? And does it in some sense determine the system? Okay. To answer this, first some simulations. So to represent the environment, the sequence H, I represent the potential associated to it. So it's the random walk with increments, the Hj's. And here are 5 independent samples under the Gibbs measure with boundary conditions plus. And here you can also already see that the behavior is quite different from the pure Ising chain, because, well, the 5 samples have decided to put minus domains here. They start exactly at the same position. Here they start approximately at the same position. Here also we have a plus domain, which is quite present everywhere. Here it's a bit different. Some of them have decided to put pluses inside this big minus domain, but actually these 3 have decided to put them at the same place, so it's really not uniformly at random. And indeed, this minus domain corresponds to a fall in S, this plus domain to ascension in S. So we will have to figure out how the potential influences the configurations. Here below is a plot of the probability that sigma n is equal to +1 as a function of n. And there you can see that quite differently from the pure Ising chain, the probability is not close to 1/2. It's rather often close to 0 or to 1. Here it's not so clear. And this corresponds to what we see in the samples. Okay. Is there any question about this presentation of the model? Please don't hesitate to interrupt if there is. And now a last definition is a continuous model, which is quite interesting because for this continuous model, there are some computations are possible. Some quantities can be computed explicitly. And in fact, this continuous model is obtained from the random field Ising chain by performing a weak disorder limit. So if you send n to infinity, gamma to infinity, and the variance to 0, and rescale the configuration sigma in a finely tuned way, then you obtain a non-trivial limit, which is essentially the same model, but now the space is continuous. So the range of the system is R, the intensity is still gamma, and the boundary conditions G and D. We start from a reference measure, which is the law of the Poisson flip process. So it's the time continuous process, which starts with values in -1, +1, and which jumps to the opposite value at Poisson rates, so at rate 1. So yeah, it just jumps at the times of a Poisson process on the real line, for example. And we started from 0 and condition it to be at D at time R. Now the pure model is obtained by modifying this reference measure according to the number of jumps in S. And in fact, it is a simple exercise to see that this yields the same Poisson flip process, but with the rate now replaced by exponential minus gamma. We have simply penalized each jump by factor exponential minus gamma, and this yields exactly this. And finally, the disordered model is obtained by adding an interaction with the realization of a standard Brownian motion. So as before, we consider a random environment, and for every realization, we consider a new measure, a Gibbs measure, defined in this way. Sorry, this should be a 0 because we defined it with respect to the reference measure. Anyway, this is not so important but the continuous model will be helpful to give us insights on the behavior of the model. and in particular for the free energy. So let me talk about the free energy. It's just here I just recall the definition of the partition function, and it can be established using ergodicity that almost surely the logarithm of the partition function divided by the size of the system converges, and that the limit is deterministic. This is an application of Kingman's subadditive ergodic theorem. The limit does only depend on gamma and on the law of H, but not on the realization of H itself. This is called the free energy. In the pure case, it can be computed because, as I said, the pure case is simple, and it's just the logarithm of 1 plus exponential minus gamma. So order exponential minus gamma. And in the disordered case, it's going to be different. In fact, before giving you the theorem in the disordered case, let me mention what happens in the continuous model. In fact, there we also have the convergence towards the free energy, but we have an explicit formula for the free energy. This where kappa. Okay, these functions are Bessel functions. It's not important to know which ones exactly, but what's important is that we can develop this expression, and the expansion takes this form, which is surprisingly quite regular. All the expansion in powers of 1 over gamma is only given by this constant here in the denominator. And this gamma em is the earlier Mascheroni constant. In fact, in the disordered case, but for the discrete model, we're going to obtain something quite similar. So under great generality, we're able to show that the decay is like 1 over gamma. And in fact, under integrability and regularity assumptions on the disorder law, we have this expansion with a rest which depends on the integrability assumptions. So in particular, if the disorder law has exponential moments, then this term is exponentially small. So we also have this intriguing behavior that the expansion in powers of 1 over gamma depends only on these two constants. So this is the variance, and this kappa is a more complicated constant. In fact, it's not understood now why the expansion is so regular. Okay, why is it so important? Why is it so interesting to know the free energy? I'm going to illustrate this quickly. So by an elementary computation, if you have never seen it, you might find it interesting. If I derive the free energy in terms of gamma, then I'm going, if I divide the logarithm of the partition function, I'm going to get in the denominator the partition function itself. And then in the numerator, the differential of the partition function, I get exactly this times the what's in front of the parameter gamma here. So, okay, this is nothing but the expectation under the Gibbs measure of the walls in the configuration. So if I divide by 1 over n, sorry, let's add a minus factor here. If I divide by 1 over n divide by n everywhere, I get the expectation of the mean, of the density of walls. And then using some convexity arguments, I'm able to take the limit here in n, and I obtain that minus gamma, minus the derivative of f in terms of gamma is equal to the limit as n goes to infinity of this expectation. So in fact, this is a very interesting information. So in the pure case, we get that the mean density of walls is 1 over exponential gamma plus 1. This is in accordance with what I presented before. And in the disordered case, the density is rather theta squared over gamma squared. In terms of the sizes of the domain walls, it means that we recover that the size here is exponential at gamma, and here it's of order gamma squared. So this is the first big disorder relevance. Okay, and now I'm going to explain quickly how we are able to estimate the free energy. So first, we're interested into the exponential growth rate of the partition function. So let's fix the boundary conditions on the left and study how this couple evolves. So the couple where with boundary plus and with condition plus and condition minus on the right. If you consider the system from 1 to n+1, you can decompose it by looking at the value at n+1 and obtain this recurrence relation. So this is the recursion we're interested in. In fact, if you consider the process ln, which is the ratio of zn plus over zn minus, so if you divide the first equation by the second, you obtain this random recursion. So ln plus 1 ln is a Markov chain where the randomness comes from the sequence hn. And in fact, you can show that this Markov chain is positive recurrent. Now, if you rewrite the first equation here by factorizing by zn plus and take the log, you obtain an expression for the log of zn plus involving this sum, where now this ratio ln appears. Okay. Now divide by 1 over n, and you see that it's interesting to apply the ergodic theorem for this Markov chain ln. This gives an expression of the limit as an integral against the invariant probability measure of the process ln. I will not write it explicitly, but you take the expectation of this expression where h is taken under the disorder law, and this quantity here in the denominator is taken under the invariant probability measure. Okay, this is I made this slide to explain explicitly where this integral expression comes from, but in fact there's a general theory. Indeed, these partition functions arise as a random matrix product. If you consider the matrices below and try to do the full product, you're going to end up with contributions that correspond to every configuration in the random field Ising chain with exactly the right contributions. And therefore, the 4 coefficients of these random matrix products are exactly the 4 partition functions with the 4 different boundary conditions. So the exponential growth rate of the partition functions is the so-called Lyapunov exponent. And there's a general theory, and what I did is just a pedestrian way of obtaining the formula for the Lyapunov exponent. So now that we have a formula, we want to analyze it, to estimate it. And the key is to understand the invariant probability measure of the Markov chain. Let me phrase it in terms of the logarithm of capital Ln. So if you introduce little ln the logarithm, then you have this recurrence relation with a function b gamma given here and plotted here below. So this function is very close to the identity between when it's in between minus gamma and gamma and not too close to them. And below minus gamma, it's going to take you back to minus gamma, and above, it's going to take you back to gamma. So if you look at this, you can understand this as a random walk. So ln with increments 2hn, but subjected to a confinement mechanism through the function b gamma. Okay. So it's quite okay. You should expect that the invariant measure should be close to the uniform measure on minus gamma gamma. Indeed, here is a simulation, and you can see that it's indeed the case. But the problem is that to understand the integral formula that we have, we need to understand very precisely how the invariant measure looks like on microscopic scale around minus gamma, so around the left side. And there's a heuristic from Derrida and Hilhorst, which is to consider 2 auxiliary processes which have infinite invariant measures. In fact, they are obtained by removing one or the other of the two rules that our process is subject to. So this gives you two invariant measures, which are quite flat asymptotically, and if you patch those two infinite invariant measures, this gives a good candidate for the true invariant measure of the process Ln. And okay, you can make sense of this heuristic and show the expansion of the free energy, which I stated earlier. Let me just mention that for the continuous model, things are simpler because instead of having a discrete random walk, which is subjected to confinement mechanism, we have a diffusion in a potential. And therefore, we have an explicit expression for the probability measure, and we can exploit the integral formula that we have and exactly compute the free energy. Okay. I'm finished with the free energy. Let me now go to results at the level of configurations, because we are able to describe more precisely the typical configurations. First, a heuristics that dates back to the 70s. Here is an instance of the potential, and we consider first the configuration which is +1 everywhere, and we consider the possibility of switching the spins between n+1 and n+l. If we do so, this modifies the energy by -2 gamma, -2 gamma, because we have introduced two rules. And this, we also have this modification because instead of counting the HJs positively, we now count them negatively. So if capital L is large, this sum is approximately distributed as a Gaussian variable with variance theta squared times capital L. And for this switch to be interesting, the overall gain should be positive. That means this Gaussian variable should be smaller than minus gamma. And this occurs with a non-negligible probability only if L is large enough. In fact, this heuristic suggests that the correct scale should be L such that the square root of theta squared L is over the gamma. So they suggest the order gamma squared. In fact, it's the same as what we obtain with the free energy. And but it also suggests that the domain rule structure strongly depends on the disorder, in the sense that the configurations will be strongly determined by what the environment looks like. Okay, the next step is to refine this argument to determine first the configuration which maximizes the energy. So let me illustrate this. As I said before, we represent the environment through the associated random walk, and our aim is to find the configuration which maximizes the Hamiltonian. And to answer this question, we have to use the notion of gamma maxima and gamma minima associated with the walk. So here is an example of a walk centered. And we are going to say that a site U here, for example. So let's say gamma is this quantity. We say that U here is a gamma maximum because I can exhibit two values, two instance S and T, such that the random walk S is maximal at U in between S and T, and the height difference between S and U and between T and U is larger than gamma. Okay, this in words, this means that U is at the top of a mountain of size at least gamma. Similarly, you can define the notion of gamma minima. In words, the bottom of a valley of size at least gamma, and this instance the gamma minima and the gamma maxima, they alternate and they break the potential landscape into ascending and descending portions, which we call gamma stretches. Okay. Now I claim, and it's elementary to prove, that the configuration which is adapted to this description, so which is equal to +1 in ascending stretches and -1 in descending stretches, maximizes the energy, so the Hamiltonian. In fact, everything I said is also true for the continuous model, and the illustration is pretty much the same. You have a Brownian motion, and you define the notion of gamma maxima and gamma minima, and then this gives you the configuration which maximizes the Hamiltonian. Okay. In fact, this construction is quite interesting, and I'm going to talk about it a bit later. But now what we're going to is that actually the typical configurations would be quite close to this maximal energy configuration. So in the end of the 90s and the beginning of the 2000s, physicists Fisher, Ledoucelle, and Montus used the renormalisation group argument to justify that this should be the case. But it's not very clear what close should mean, and we're going to see how we can make this rigorous. Here is a simulation. In fact, it's the same simulations as I showed in the beginning. This is the environment, and this is the probability that sigma n is equal to +1. And but additionally, I've put vertical lines for the gamma maxima in red and gamma minima in blue. And as you can see, they correspond to where the probability seems to switch from 0 to +1 and from 1 to 0. Okay. This is with a small value of gamma. Gamma is equal to 5, but now I'm going to show you a simulation with gamma equal to 20. And then you see that this behavior is even sharper. So the probabilities are really close to 0 and to 1, and they really switch at the position of the gamma extrema in this simulation. And now with gamma equal to 100, this is even sharper. Okay. So our result is for gamma.
Sorry, can I interrupt you?
Yes, of course.
Sorry, can you come back to the previous slide? Yes, here. Okay. So if I look at the second graph between, I don't know, 80 and 175, you have some kind of excursion which are going up.
Yes, that's right. And in fact, this corresponds to the simulations which I showed in the beginning. We saw that in these regions, so it's really the same sample. In these regions, there is some possibility for the system to introduce plus domains with a probability which is bounded away from 0 and to 1.
Yes, I understand, but afterwards, these excursions are disappearing. It is because you take a gamma large, or?
Yeah, it's because gamma is large. I forgot to say that we're mainly interested into gamma large, and the claim made by the physicist is as gamma goes to infinity. They speak of asymptotic.
Yes, it in the numerical simulation in the graphs which are after, it is gamma is what? It is
gamma is 20 here, and already these incursions are here. There is one. In fact, it's quite easy to understand why. Here, the maximal energy configuration switch is here, but there is another maximum here which is quasi at the same height. So it may be interesting for the configuration to switch to decide not to switch at this position, but rather at this one. And in fact, this explains why here there is also there is a small possibility to have pluses in this region.
And do you have some result which permits to say that in some sense this graph of SI is converging to this jump Markov process between 0 and 1 in some kind of limit?
So the level for the probabilities?
Yes. I mean, it seems that at the end you have some kind of a jump Markov process between 0 and 1.
Well, yeah. Well, okay. The instants here are determined by the gamma extrema, and I'm going to talk about them in a moment. And then,
okay, I can wait.
so
Okay.
the distance between these vertical lines is understood, and then we kind of we have arguments for the fact that in between the probabilities here it's very close to 1 and here it's very close to 0. Okay, so
Okay, thanks.
exactly I was going to speak about this process of gamma extrema. So it breaks, in fact, these times are not stopping times, however, they are renewal times. You can see this using fluctuation theory, and this means that the potential is broken into portions which are independent, and the ascending portions are identically distributed, and the descending portions are also identically distributed. Okay, so this is quite interesting. So here we have, sorry. So we have independent objects that make up this the random walk. Okay, we may wonder about the typical height and length of these gamma stretches, and in the continuous case we have an explicit law. So by Brownian scaling, the height and the length at scale gamma, they scale as gamma over gamma squared. So you can focus on the law for gamma equal to 1. And in this case, the joint law is explicitly known thanks to work by Neveu and Pittman in the 80s. And in particular, the height h1 is distributed as 1 plus an exponential variable. They use excursion theory for the Brownian motion. And in the discrete case, we don't have an explicit expression for fixed gamma, but we have an asymptotic result. So if you perform the same Brownian scaling, you obtain the convergence towards the variables of the continuous case. And this is simply an application of Donskis theorem. Okay. Okay, now there's an important consequence for us is that by definition, H gamma here is larger than gamma, but the excess is also of order gamma, so it's typically quite large. And this is going to be very useful. This means that if you start from this configuration which maximizes the energy and decide to switch this whole domain of minuses to +1, not only is this not interesting because it decreases the energy, but in fact it's going to decrease it by a large factor. So it's really not interesting. And this is a simple argument for, I mean, a sketch for why indeed the configurations will really look like the Fisher configuration. Okay. So here is the theorem. If we denote by sigma f the configuration which maximizes the energy, then we can show that the overlap between sigma taken under the Gibbs measure and this configuration sigma f, this random variable converges in distribution towards 1 minus epsilon gamma. So a constant, this is a negodicity result. And in fact, this constant decays as gamma goes to infinity. So it's upper bounded by log gamma over gamma. Okay, so this is a almost sure result. So for every fixed environment, this convergence holds. Okay, here are a few observations. So if you prefer to state this in terms of overlap between two independent configurations, then you can easily obtain that the overlap will also converge in distribution towards a number which is which tends to 1 as gamma goes to infinity. In the case of Gaussian disorder, we're able to actually compute the limiting overlap between two independent configurations and see that it's 1 minus order 1 over gamma. So this implies in the case of Gaussian disorder that epsilon gamma is at least of order 1 over gamma. So our bound here is quite sharp. And well, during the questions, I can explain where this 1 over gamma comes from. And finally, in a previous work in 2024, we showed the same thing for the continuous model, that the configurations of the continuous model are very close to the maximal energy configuration with respect to the overlap. Okay. I'm going
Sorry, can you recall what is a continuous model?
yeah, the continuous model is pretty much the same, just that the space is continuous. So you have a configuration sig S valued in -1 and +1, and it's the reference measure is a Poisson flip process, so it switches from -1 to +1 or 1 to -1 at rate 1, and you make a disordered version by adding by penalizing the presence of walls, of jumps by gamma, and by adding an interaction with a Brownian motion.
Okay.
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 So it's really, you can think of it as the same kind of the same model, just that the space is continuous, but the stakes are not the same in terms of proof, because in the continuous model, some things are more computable, but technically some others are more difficult. Okay. Okay. And now I'm going to give a small idea of the proof. So you have, okay, the starting point is to express the probability we're interested in, using two processes, and the aim in the end would be to show that this probability is close to 1 in ascending stretches and close to 0 in descending stretches. Okay, so if you consider the system between 1 and capital N, and you consider what's going on at little n, here you should, okay, in the numerator, you should consider all the configurations which have sigma little n equal to +1. And in fact, this decomposes into two subsystems. So you get this product of partition functions. In the new denominator, it's the same. You have the configurations with sigma n equal to +1, and the configurations with sigma n equal to -1. Now let's divide by the numerator, and you obtain this interesting form, because we have ratios of partition functions with the boundary conditions which vary. Here the right boundary condition varies, and here the left boundary condition varies. And this ratio we have already studied before. It's the process capital Ln, which I mentioned earlier when talking about the free energy. So if we introduce the logarithms, little l and little r, we have to understand this. And the aim is to show that with large probability, what's inside the exponential is large, and it's positive in ascending stretches and negative in descending stretches. I'm going to argue why it's large. In fact, if you remember, I've studied this process. But this process L evolves like the process Ln I took before, and so if you're far away from the boundary, it's going to be distributed essentially under the invariant measure, and this invariant measure is close to the uniform measure on minus gamma gamma. So this variable is typically of order gamma. It's the same for this R. This process evolves, in fact, as n. It evolves backwards in n, in the sense that it incorporates the information coming from the right, and it evolves in this direction. The recursion is backwards, but also this will be of order gamma if you're far away from the boundaries. And this is order 1, and the 3 are independent. So you can argue that most of the time this is very large, okay, of order gamma. So it's not going to be close to 0. And for the sign, we have to develop an additional argument, which is based on a 0 temperature analog, but I won't detail. Okay. To conclude, I will take just 5 minutes to talk about the unbalanced disorder. So the case where now the disorder is not centered. So let's assume the expectation is positive. So now the situation is different because our environment is a random walk with a drift. So typically this should be like this. In the Brownian case, you replace B by a drifting Brownian motion. Okay. You can still look at the gamma extrema. So let's say gamma is here. If you decompose this in terms of gamma extrema, okay, let's say you obtain something like this. In fact, your gamma stretches will be quite different. Well, there's a bias towards plus. So these will be very large. In fact, exponential 2 alpha gamma. And the descending stretches will be much rarer. So yeah, it's still relevant to consider this configuration because it still maximizes the Hamiltonian. But it's not. It won't be true that. Okay, let me just take some time. So the statistics of the gamma stretches are also known for this drifted case, at least for the continuous case. So for the Brownian motion, we have these things that I claimed here, and the height of the descending stretches are distributed as a gamma plus NXS, which is now of order 1. Okay, in the discrete case, we don't have exactly these results for now, but we expect them to be true. But the problem is we can't use Danska's theorem anymore to derive from the continuous case the discrete case because of this drift. So it's yeah, and in fact the parameter alpha, which would intervene in the discrete case, is not the mean of H as you could expect, but it's rather the real number alpha which satisfies this equation. Okay. We have some estimates on the free energy. However, so some things can be made, but now the Fisher renormalization group does not manage to capture the correct behavior of the free energy. Let me explain this in a few words, just to give you the idea. As I said, these descending stretches have a height which is simply gamma plus an excess of order 1. This plays a huge role because this means that typically it will be gamma plus some constant. And this means that if I consider the configuration, the maximal energy configuration, and decide to switch it to +1, then this will result only in a modification of the energy, which is twice C. So it's of order 1. So in fact, these two configurations have weights which are comparable. So what I want to say is that deciding to put this minus domain or not to put it is they have probabilities which are bounded away from 0 and to 1 generally. So you should add an additional. In fact, the right way to describe this is not to say that we compare with a deterministic configuration, but rather with a simple model where for each descending stretch, we add a Bernoulli variable so there's some randomness. Okay. And indeed, Fisher and collaborators do not claim that their renormalization group work. They claim it only works asymptotically in the limit where the mean goes to 0. So we don't really know what this means. So, okay. this is yeah, this statement is too elusive. Okay, and now I'm finished, and I thank you for your attention.
Thanks a lot, Orphée. So are there questions?
Yeah, I have a question about this epsilon L.
Yeah, this one.
Yeah. So like if is it right to think of this as the kind of the fraction of sight where the probability of sigma L, which is, sigma n being equal to plus, is neither close to 1 nor close to 0?
Yeah, in fact, we have an expression for this this 1 minus epsilon gamma. So you should define an infinite volume system. So a system on the whole of Z. So okay, this means you extend your environment to the whole of Z, and you send the two boundaries of the system towards infinity. You can define an infinite volume system. This is quite easy in this case because we're in dimension 1. You can also define the Fisher configuration, so it's the ground state configuration on Z associated to H, and then the expression for 1 minus epsilon gamma is the probability under this infinite volume measure of having the configuration at 0 equal to the configuration at okay. So in terms of epsilon gamma, it's different from the Fisher configuration. And you should take the expectation under the environment. So yes, indeed, this is an ergodicity result, and you can interpret it like this.
Okay, so yeah, I'm surprised by this 1 over gamma. So I guess that if you take the Fisher configuration and if you take the sides that are very close to like the barriers you have in the Fisher configuration, these things, they will typically be like they will give a contribution to this sum, right?
Yes. Okay.
Because
yeah.
you can make the switch between plus and minus. You can move it from to a finite distance. This won't change very much the weight of the configuration.
Yeah. So there are different behaviors in play. So indeed, around an extremum, the actual the true configurations will pick a neighbor. They won't change exactly at this position, but they will switch somewhere around. And in fact, the position of the spin switch is distributed as a variable in this potential. So, for example, it can fall here. So this yields typically another one displacement of the wall. So this would contribute
1 over gamma square, right?
1 over gamma squared, exactly, to the overlap here.
Okay. So what's the main contribution?
In fact, yeah, in fact, the mean contribution comes from those stretches, which are quite rare, where the height is gamma plus order 1. So if you remember, this is gamma plus gamma times exponential of 1.
Yeah, okay.
But with the probability gamma, with probability 1 over gamma, of order 1 over gamma, it's going to be instead gamma plus little o of 1. And in this case, putting minuses here or remaining at +1, they are both comparable. And this
Yeah, like in the biased model, right?
Yes, that's it. Yeah, exactly.
Yeah.
So
Okay.
So there are further. Okay, I have now a finer description, but this needs to be written down. You should take into account these stretches that balance that have a height which is quite close to gamma. By the way, in the same sense, inside an ascending stretch, for example, typically the biggest drop is uniform on 0 gamma. So also there you could have that with probability over the 1 over gamma, that this drop is in fact quite close to gamma. So you should take into account these rare events if you want to get a final description.
Okay, and this is a bit vague, but in the free energy, you have this, basically the free energy expansion to any order in 1 over gamma square, right? In 1 over
Yeah.
gamma.
Yeah.
So do you have an interpretation for all the terms that appear?
Actually, yes and no, in the sense that I have kind of a control. In fact, I now have a way to, so it's not published yet, but I have a way to understand, okay, to have a similar, a similar theorem, but I replacing the Fisher configuration by a random configuration, which is, however, quite simple. I would be able to get any error here, which is of order 1 over gamma to the n for any. Okay, I could, in some sense, understand everything that is going on up to order 1 over gamma to the m.
Okay.
So in the free energy, it's also quite true, but so I have expressions for the coefficients in some sense in the expansion. So of the free energy, I have some interpretation, but I have no way to see why they are so simple as just theta squared times kappa to the k minus 1, I think. So it's not fully clear why it's so simple that we have only these two constants.
Okay, thank you very much.
Thank you.
More questions? Concerning
Okay, sorry, no,
please, Cedric.
go ahead. No, go ahead.
Just concerning the unbalanced disorder.
Yeah.
The one thing I didn't understand was if the drift was constant or dependent on n.
The drift is constant because we work with a fixed disorder law, and so it's a fixed drift. It's a fixed mean.
Yeah.
And then
then the continuous. I mean, usually to get a continuous model that gets a drift like this, alpha t, you would have a bias that is decaying like alpha over root.
Yeah, that's correct. So the continuous model is obtained as a weak disorder limit where we take, so for example, we take so if you want to know exactly the weak disorder limit, we take is this one, something like this. So we pick a parameter delta, which is positive and we're going to send to 0. The size of the system is delta n over delta squared, sorry, n over delta, and we use HNs which go to 0. They are delta times omega n plus alpha delta squared. With omega n some i.i.d. sequence which is centered and with variance 1. I think that's it.
I see.
Indeed, this is what yields the continuous model with a Brownian motion with a drift.
I see. Thanks. Cedric?
Yes, sorry. Maybe I will ask again the same question. In
Yes.
fact, if you come back to the first slides, it's with the pictures, this probability of sigma n is equal to 1. Yes. This
Yeah.
kind of pictures. So, do you have some results saying that in some suitable scaling limit, you are converging to some Markov process, pure Markov process between 0 and 1? I mean, for example, the distance between the domain walls is exponential distributed in some limit.
Oh, no, okay. No, no, okay. Okay. These are the gamma extrema, and they are so the distance between them are i.i.d, but they're not exponential variables. They're so these are the length of the gamma extrema. So they are of order gamma squared. But this here is distributed as in fact the first hitting
As
time of
exponential.
it's not exponential. It's distributed as the first hitting time of 1 or -1 by a Brownian motion started at 0.
Yeah, but you cannot perform some scaling limit in order that it becomes some kind of exponential, or no? Because okay, sorry. When I look at this picture, it is very similar to something that I was looking at which are SDEs with strong measurement, which appears in quantum mechanics, and the
Okay.
graphs are very similar. You have some SDE which is living between 0 and 1, and in the large noise limit, it's converging to some Markov gem process between 0 and 1. But you have also some kind of spikes which appears, like in your previous picture when gamma is a bit smaller. I don't know, it seems to be a bit similar, but
Yeah. Yes. Well, I guess so. We have an explicit description for the times between the extrema, and then we have arguments which say that in between between a minimum and a maximum, the probability is very close to 1, and between a maximum and a minimum, it's close to 0. So there is we could state a theorem in terms of I guess score topology or
yeah,
but
but okay. So maybe I will send you some email because
okay.
it is
Okay.
maybe not very clear what I want, but it is very similar to some other things.
Okay.
Okay, thank you.
Thank you.
Okay, so there are no more questions. Let's thank Orphée again. Thank you. Can we continue next week? Thanks, Orphée. The next time.
Thanks. Yeah. See you.
Bye-bye.
Bye.